Okay. So today I will give another interpretation of the dimension for a ring, which is convenient because you can, this way you can work with things like local ring given by generators and relations and immediately see the dimension. So okay, so I will start with the abstract notion of filtration. So filtration on a vector space is just a family of subspaces, but we're interested on a ring, so I would fix the notation and conventions. We have a ring, then we have A contains, so we can identify A with the 0 step of the filtration, F0. It contains F1, contains F2, and so on. And these are vectors. So if it is a ring just over Z without any groups, without any vector space structure, it will be subgroups. But typically it will be ring over K, and this will be K vector spaces over K. So this is subspaces, and this is called so Fi is multiplicative filtration. If Fi times Fj belongs to Fi plus j. So example, is you take M some ideal, maximal ideal or just any ideal, and you take Fi is M power I. This clearly satisfies this relation. By M power I mean an ideal which is generated by products of I elements from this ideal. Okay. Now, if you have X inside Fi, here it was, I think like A1, A2, A1, A2 inside Fi, B1, B2 inside Fj, and now we can assume that Fai minus A1 minus A2 is equal 0 modulo Fi plus 1, which is the same. A1 minus A2 belongs to Fi plus 1. And the same with B2. B1 minus B2 is equal 0 modulo Fj plus 1. In that case, A1 B1 is equal to A2 B2 modulo Fi plus j plus 1. So it is clear that this product belongs to an element of filtration Fi plus j, both of these elements. But then it turns out that they are equal modulo this, and the reason is clear. You write A1 B1 is equal to A1 B2 modulo Fi. This is where A1 belongs, and then f j plus 1. This is where b1 minus b2 belong. So this is equal to, well, that belongs to f I plus j plus 1. Well, on the same reason, if you write a1 b2, this will be equal to a2 b2, modulo the same space. Good. So this means that the multiplicative structure is well defined on the space f I modulo f I plus 1. You multiply that by f j modulo f j plus 1, and this multiplication goes to f I plus j modulo f I plus j plus 1. Now, definition: associated graded ring of the filtration f is direct sum of f I quotient by f I plus 1 for all I from 0 to infinity. You can define the space even without multiplicativity, but then it will be just associated graded vector space or a group if you work with a billion groups. But what is important that this is a ring. And of course, you need to check that it satisfies the ring axioms, but it is almost clear. I mean, associativity is clear, commutativity and distributivity also clear, just from the same axioms for a ring. Okay. Yeah, what is also nice that you can associate such a algebra to any ideal. So if you have I inside a ideal, then a direct sum. So we use convention A0 is equal to I0 is equal to A. It will be from I equals 0 to infinity, I power I quotient by I power I plus 1. This is a ring for the same reason as here. It is called associated graded ring. Graded ring of the ideal I. There are situations when this ring is not very good, but typically it's good. So in many situations it's just equal to the ring you started from. For instance, if you do it with polynomials, so you have a example. You have A is C of T1 dot 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 Tn, and the ideal I is generated by T1 dot dot Tn. In that situation, you would have I power k is polynomials of degree well, it's better to say sum of monomials. It's all sums of monomials sums of monomials of degree starting from k. So, for instance, I is monomials of degree 1, 2, 3, and so on. I square is monomials of degree 2, 3, and so on. And then you take ik by ik plus 1. What remains only is monomials of degree k. So it's what is called sim k of the variables t1 to tn, which is the same as all the space of generated by all monomials of degree k. And then it's clear that if you multiply two monomials of degree k, obtain monomial of degree k, and monomials of bigger degree go to monomials of bigger degree, and this means that the corresponding graded ring, so you have direct sum of ik to ik plus 1 is the same as direct sum of sim k of t1 to tn. So it's sum of all monomials, and this is the same as polynomials. Sorry? Yeah, you would just obtain polynomials. This is symmetric powers. What was the question? This was the question?
No, it was just a comment. That this associated graded ring is like a ring of formal power series.
Yeah, well, not really, because it's not formal power series. Its completion is formal power series, and it is more like polynomial ring.
So
It's
for example, for a ring of holomorphic functions,
you would have polynomials. Yes, no, maybe it's a good idea to check this. Let's do that for holomorphic functions, or for any power, in fact, for any ring of like formal power series, the same argument will work. So take OX CNX 0. It's the germs of holomorphic functions, which means that you have a small neighborhood of 0, and you consider all functions there, and then take the limit over smaller and smaller neighborhoods. This is something we have already considered several times. And then there's from germs, there's a natural map to formal power series. T1, Tn, and this is homomorphism. It takes a function and maps it to its Taylor series. So here, when I write two brackets, I mean that I allow to take not finite sums, but infinite sums of monomials with degree going to infinity. Okay, and now if we take, again, I will be the ideal of a point, so all functions, it's a maximal ideals, vanishing in 0, then ik is all functions with derivatives less than k vanishing. So for instance, I2 is power series starting from, so it will be like A1 T1 squared plus A2 T1 T2 plus A3 T2 squared plus B1 T1 third plus and so on. This will be, so your ideal starts from ideal power. If you take I power k, it is function with Taylor expansion starting from power k. This implies that I k quotient by I k plus 1 is actually the same. So we were interested in Taylor coefficients, number k, which are homogeneous of degree k, up to all the rest of Taylor coefficients. So this is the same as sim k of T1 dot Tn. And this implies that the corresponding associated graded ring is again a polynomial ring. So this is polynomial from T1 dot Tn. Even in that situation. It's the same true, the same argument works in smooth case if you use, it's what is called Adamar lemma, that the map to Taylor series, the kernel of the map to Taylor series is just functions which have all zero derivatives, and it is injective up to a higher degree. Sorry, surjective up to higher degree. Okay, so this is the ideal. And then this is not that extremely typical situation, but almost typical, which is something we probably will discuss tomorrow. And then what else? Yeah, but there are examples where we start with a ring, for instance, which has no zero divisors, and you arrive at a ring which has zero divisors. Maybe I can give you an example. So we have an equation, T1, T2 plus T3 power n is equal to 0. What is yeah, it's not very hard to see that if you have a ring A quotient by this equation, so it's by an ideal, so this is P, by quotient by ideal generated by P, this has no Z divisors. Well, I assume that n is at least 2. Okay, but if you take the corresponding ring in associated graded ring, and again we take an ideal, yeah, sorry, A is polynomials, of course, C of T1, T2, T3. However, if you consider the corresponding quotient, it's not hard to see that you would have T1, T2 equals 0 in associated graded ring. Yeah, you take, of course, as usual, you take ideal I generated by T1, T2, T3. then this P modular, so P belongs to I, and P mod I square is equal to T1, T2 is equal to T1, T2. Right? Then, if you take the associated graded ring of this, let's call this A, you take the inside A, you take direct sum of I quotient by IK quotient by IK plus 1. And this is a principal ideal. And the quotient of principal of, if you then the corresponding ideal in that ring is also principal generated by P. Because all elements which, so this is equal to polynomials well, you have to compute this, but it's not hard. It will give you polynomial ring quotient by this polynomial P0. But P0 obviously has zero divisors. I mean, this quotient has zero divisors because T1, T2 is equal to 0 in this ring. So you see, when you pass to the associated graded quotient, bad things might happen. Okay. Yeah, so if you have a Noetherian there was something which, in fact, we had already discussed that in maybe lecture 6 or around. But it's still worth repeating that if you have a Noetherian ring, so A Noetherian, then you have GR, well, you take some ideal I inside A. It should be local. Yeah, when you say Noetherian local ring and you take associated graded, by default, if you don't specify ideal, this always means maximal ideal. So this maximal ideal, and you take direct sum IK by IK plus 1. This is GR A, associated graded ring. And claim that this associated graded ring is finally generated. Well, the idea is, suppose you have an, first, you prove that it is Noetherian. And well, suppose it's not finally generated. Then you would have an infinite family of submodules in this graded ring. But then for each submodel in the graded ring, you can obtain a submodel for each ideal in the graded ring, we can obtain ideal in A by, because if you have I inside of this direct sum GR, well, I already have, so I have J inside GR A. And we can assume that, again, if it's not finally generated, you would have an infinite family of ideals, infinite chain of ideals, which are also graded, means that they are generated by elements which sit in the graded components. So you have infinite family J1, sits inside J2, sits inside, and so on. Graded ideals. And for each of these ideals, you can take pre-image. First, you take suppose you have an ideal inside your. So you have your graded ring. Let's consider it A0 plus A1 plus A2 plus and so on. And you have an ideal, which is I1 here, I2, I3, and so on. Then you have a map from your, well, already have, let's call it J. So you have AI. AI is power of your ideal. AK is IK quotient by IK plus 1. So you take a pre-image of this into that. And then you take, this belongs to I. So this here you have I1, I2. Here you have J2 goes to I2 power I3, and so on. So each of these graded components gives you a subspace there. And since they are closed under multiplication, this will give this ideal obtained from that ideal will be actually, this subset will actually give an ideal. It's closed under multiplication by elements of A and by addition. I assume that, no, it's not a sum of ideals, it's sum of graded subspaces. I start with a graded ideal, which is sum of graded subspaces. Yeah. And if I have such an ideal, I obtain an ideal in the ring. If you have an ideal here, this gives you ideal in A. Like that. So every time you have an ideal in a graded ring, associated graded ring, this gives you an ideal in a ring by taking these pre-images. So if you have infinite chain of graded ideals, this gives you infinite chain of graded ideals inside the associated graded ring.
Why do they institute the nested family? Because then you put like different intersecting ideals.
No, if something, if you increase this space will also increase. So if you strictly increase this space, so for each subspace in there, this gives you a subspace in I1, because you have a surjective map from say IK to IK by IK plus 1, and to take the pre-image. So if this, and your ideals are generated by these pre-images. So if you have an ideal J, here you have an ideal, then you take pre-image of each of this element in the corresponding, so J1 goes to I, J2 goes to I square, and so on. And these preimages generate you an ideal in the ring A. Well, so you have a map from I power k to ak. Ak is I power k quotient by ik plus 1. If you have an subspace jk here, you take its preimage, so let's call this pk. You take pk minus 1. Pk minus 1 of jk. So if you have this kind of ideal, you take direct sum, well, just sum, sorry, sum, but in the sense of taking sum of vector spaces of pk minus 1 of jk for all k, for k starting from 0 to infinity. Well, from 1. So this gives you an ideal in a ring from any ideal in the associated graded ring. And if you have an increasing you increase your subspace, say increase jk, then this preimage would also increase. So this implies that every time you have an increasing chain of ideals in a graded ideals in a graded ring, this gives you an increasing chain of ideals in A, so it's really Noetherian. So preimage of, and Noetherian, if you have a graded ring which is Noetherian, it's actually finitely generated, something we have discussed already. If it's not finitely generated, you just take, suppose it's not finitely generated, you take an ideal generated by one element, generated by two elements, generated by three elements, and you arrange them in such a way that they increase. And this would give you an increasing chain of ideals. Indefinitely increasing because because if this chain stops, your ring is finitely generated. Should I repeat this? This we had that.
Probably I missed it. So it's a map, natural map from a ring to its associated graded ring?
This is not a map. It doesn't exist.
No,
there's no such map. It doesn't exist. But you can always, if you have an something, if you have say an ideal in a ring, you can try to form an ideal associated graded. This typically you will succeed. Of course, this new ideal associated graded can be bad. You can't expect that if you have an increasing chain of ideals, this would give you an increasing chain of ideals in associated graded ring. In other words, associated graded can be Noetherian even if your ring is not Noetherian. But converse still works. If your associated graded ring is, if your ring is Noetherian, associated graded is Noetherian. And the argument is very standard. It's sort of exercise type argument. So you have any ideal in a associated graded ring gives you an ideal in a ring, and if you increase your ideal, this ideal in the ring would strictly increase. In fact, there's injection between these ideals and that ideals. Okay. Now, if you have a graded, you can do, if you have a graded ring. So what is generally a graded ring? Let me give you Have I? Well, probably I had the definition. The previous. Let me give a definition of graded ring and graded ideals, graded models. The definition. If you have A, which is direct sum of A k from k equals 0 to infinity, and A I, A j goes to, this is a product, is inside A I plus j. This A, usually you write A star, is called graded ring. And suppose you have n, which is also direct sum from mi, from I equal to, well, here it can be actually integer, I in z. But since we are working mostly infinitely generated, this will be something non-negative, or maybe non-negative minus n or something. It's graded model, a model, if M is a model, and in addition, you have and a k m L sits inside m L plus k. This is action of ring on a model. Okay. Yeah, and there is a trivial claim. Suppose you have A star is finitely generated graded. Algebra. Well, it's usually you assume that A0 is subfield. Then it is finitely generated algebra over this field. And then you have n finitely generated A model. Then dimension of mk is finite. Well, this is because m is quotient of direct sum of free models, and for free models it's also true. And take a quotient, these dimensions can only decrease. Okay. Now I have this exercise, which I will be using in a minute. Exercise, which is high school level. In fact, I think it's given in some high schools. You have P of n. P is a function. P from like z positive to z, a function. And then we have a Q is a polynomial. Q is polynomial. And P of n minus P of n minus 1 is equal to Q of n. Then P of n is polynomial for n very big. Do you think anything about this exercise? Well, the idea is sort of simple. Yeah, we assume that this is true for n sufficiently big. this is true for n. So for all n starting from some very big number, this is true, then this is true. Why this is true? Because we start with this very big number, and then you take p of n plus n small is sum from I equals 0 to n. P, so this is p of n plus sum from I equals 0 to n, q of n plus I, right? It's because the difference between numbering, between p of consecutive numbers is q. Okay. And for any polynomial, this sum is polynomial in n. This is, you can just check that for for powers. So you take t power n plus t plus 1 power n plus and so on plus t plus n or power k, for instance. And you consider this as a function on n. So to prove that it is polynomial in n, for instance, you can just take a derivative in k and use induction. If you take derivative in n, right, or in t. Yeah, take derivative in t and use induction, right. So you suppose you know that this is true for power k. It's clearly true for k equal 0 because 0 plus 1 plus and so on plus n is n times n minus 1 by 2. So this statement for k equals 0, this is true. Or for k equal 1, this is true. And then for each k, this is integral of the same formula for, well, you take a derivative and you check using induction. Well, it's not real derivative, it's almost derivative, yeah. But it's very close. Yeah, so using induction, you can check this, solve this exercise. Okay. What else? Finally, I will have Hilbert function. So definition. Suppose you have n star is a finitely generated A star model graded. Then you write Hm of n is dimension over A0. A0 is a field of m power n. So this is nth graded component, which is considered as finitely generated, as finite dimensional vector space over this field. By this claim, it's finitely dimensional. And I'm going to prove the following non-trivial theorem, that this function, Hilbert function, is in fact polynomial. Is polynomial for n sufficiently big. So let me give you an example immediately. So example example, you have C of T is your A. It's a graded ring. The graded is given by degree. So AK is just T power K. It's a vector, one-dimensional vector space. And you can take any model over it. For instance, you can just take T power K, C of T. This is an ideal. And then its Hilbert function will be H, this is M, Hm of T, of N, is equal 1 if M is M, N is starting. So the zero, the smallest graded element is has gradient K, right? Because it's K dimensional. So it starts with K, it's 1, otherwise it's 0. So this is why it is polynomial, but not for all values. It's constant function is a polynomial, but it's a polynomial only starting from K. Before that, it's not a polynomial. Okay, and this is the same way you can do this. Examples of Hilbert functions which are polynomial for big but not for small, for other degrees and other polynomial rings. You can play with it. Okay, I'm going to prove this theorem now. It takes some work, but it's not very complicated. In fact, we're interested in that result only for rings. So only for the case where M is a model over M is equal to A. And this was, of course, the main example and the main motivation, and I don't think anybody did it for models. But then people realized that for models, the proof is actually simpler. Even if you want it for rings, you should do it for models. And then they actually defined graded models and started doing this for models because it simplifies lots of things. It's a bit like when you prove a noetherianity. You prove it, you are interested in noetherianity for finite relatedness of ideals, but in fact it's much easier to do it with models. Okay, so the first step, suppose you have 0 goes to M1 star, goes to M2 star, goes to M3 star, goes to 0 is exact sequence. So when I speak of morphisms or homomorphism of graded model, I mean the homomorphism of models over a ring, which is also compatible with grading. So it maps a component of gradient K to a component of gradient K. This is the category of graded models is like that. The all morphisms respect the grading. So in that case, we have HM1 of n plus HM2 of n is equal to plus M3 is equal to M2 of n, clearly, because this exact sequence gives the exact sequence of vector spaces for each degree, right? Okay, so if say M1, M3, well, if two of them are, so if it is polynomial HM1, HM3 is polynomial, then HM2 is polynomial. Of course, for n very big. For negative, you won't expect that to be true because it's typically 0. It's finally generated, so the degree starts from something, and for very big negative values, this function is definitely 0. Okay, so this means that you can always reduce everything to submodels and quotient models. For instance, suppose I have a model generated by k vectors, M2. Then you have a submodel generated by one vector and quotient models generated by the rest. And so you can use induction by the number of vectors which generate your model. If you can do it for just model generated by one vector, you can use this exact sequence and do it for all models. So let's give this definition, step 2. So a model M со звездочкой is called cyclic. It's like cyclic group. In fact, cyclic groups are precisely the models which are cyclic. Is cyclic if M star is generated by one vector, by T inside M star. In other words, which is equivalent, this is equivalent to M star being equal A star quotient by I star. So this means that your model is a quotient of A by some graded ideal. It's equivalent. Okay. Yeah, and it will suffice to prove this theorem only for cyclic models. It will suffice to prove that Hm of n is polynomial for M cyclic. Am I clear so far? Good. So again, we were probably interested in polynomiality for just the ring over its, considered as a model over itself. So we're interested in how the dimension of graded component grows. But it turns out that if we prove that it is, well, that this function is polynomial for all rings, we'll prove it for all models and vice versa. Okay. Now we have this exact sequence. Step 4. You have, let's denote, consider an element A inside A1. And LA is a map from MK to MK plus 1. So it's not really a morphism of models. It takes a model to the same model with the gradient shifted by 1. Takes M to AM. It's a multiplication by A. I don't see why it is 3. It should be 2. Ah, right, it's 3. It's step 3. Okay. Now you have exact sequence. 0 goes to kernel of LA. goes to M star, goes to M star plus 1, goes to cokernel. Goes to 0. Cokernel of, so it's M portioned by AM. But keep star plus 1 because this multiplication shifts everything by 1. Suppose we proved that Hilbert function is polynomial for that model and for this model. Then we can use this exercise. So suppose if H kernel of LA and H M star, well, cokernel of LA is polynomial, then you have, let's call this H M of N plus 1 minus H M of N is equal to H. So this should be the same sign as that. If you have an exact sequence of 4 terms, you can always sum their dimensions of these vector spaces to 0, just to take plus, minus, plus, minus. This is true for the exact sequence of 3 terms, but then every exact sequence of n terms can be split into a sum of exact sequence of 3 terms. So this, if you have an exact sequence of vector spaces, of any number of vector spaces, you take their dimensions, sign plus, minus, and it will be 0 as well. Like something we already had here, that the sum of dimensions sums to is 0. So this gives you, this goes with minus, this gives to plus, so it's H kernel of LA minus H kernel of cokernel. Okay, so we assume that this is polynomial, then we can apply this exercise, and we obtain that then Hm of n is polynomial for n very big, of course. So here is polynomial again for n very big. Okay, so we can, this is, the idea is to use dimensional reduction because this kernel, in fact, rings over a smaller, there are models over smaller rings. For instance, here, the multiplication by a x by 0. And so you have a subring, which is a quotient of something which, well, so and this model is actually cyclic. The cokernel is cyclic, but it is cyclic over a ring which is much smaller. It, for instance, A acts on this cokernel by 0. So it's a quotient of our ring. So this gives a reduction by, then you can use induction by dimension. This is the idea of the proof, and that now I can proceed to the proof, but maybe I should make a break. Temos intervalo para 5 minutos. So I have to finish what we started, namely that we have a local ring, well, graded ring, finally generated. We have a finally generated model over this finally generated ring, also graded. We have its Hilbert function, and we want to prove that this Hilbert function is polynomial for very big values of n. And what we did so far, that we built everything. So first, we reduced everything to cyclic models using exact sequence, and using another exact sequence, we reduced everything to smaller models. So let's do now dimension induction. So the first step of dimension induction is something we have already discussed. So step 4 now. Step 4. So if you have one generator, so if A1 is 1, then your ring is polynomial, or find the quotient of polynomial. And then, as we had already discussed, the dimension of some Hm for cyclic M, cyclic, Hm of n is constant for n very big. Typically, it's 0 or 1. Well, it can be polynomial, or it can be quotient of polynomial. If it's a quotient polynomial, it's just 0, because it's fine dimensional. So all A models finally generated are also fine dimensional as vector spaces. But if it is polynomial, then it is either a quotient of polynomial by an ideal, then it is again fine dimensional, because a quotient of polynomials by a non-trivial ideal is fine dimensional vector space. This is something we have discussed already. And then if it's just polynomial, then it's 1, 1, 1, 1, 1. Okay, so this was the base of induction. Now let's do for so what is our we do induction in dimension of H1. So suppose step 5, suppose that Hm of n is polynomial for n very big, of course, when M is B star model. M star, it's a great model, is B star model. And dimension, we always assume that our rings are generated by A1. So this is part of the assumptions. I think it was stated in the beginning. Here I didn't say it because here A generated by A1. This is assumption. You need to do it. Otherwise, in fact, you can easily have counterexamples. Okay, but fortunately, you will see that associated graded rings of local rings are always generated by A1, so it's not a very restrictive assumption. So this is B star model. Dim B1 is less than K. Need to show that Hm of n polynomial for big N when M is a model and a dimension of A1 is K. This is our step of induction. And And for that, we write this exact sequence, which is already there. So the ring A star quotient by A. Okay. This is a quotient ring. It's also generated by A1, but A1 for this ring is smaller. So the first component of this is just A quotient by A1 quotient by A. So it has smaller dimension. So this this means that H of A quotient A plus 1 star plus 1 quotient by A star is polynomial for n very big. Now the first kernel of LA is typically 0 because usually you can make assumption that your ring has no zero divisors. But if it has, then it is a kernel of A of LA is the set of all x inside our ring, such that AX is equal to 0. This is an ideal. And then you can again use induction. Because it's not only an ideal, you can also obtain as a quotient because it's, well, I will leave it as an exercise to obtain this ring as a quotient. In fact, not only as a sub, this is not only a submodel, but a quotient one. You need to take a quotient over all so this will be a ring over, well, I'm not going to explain it now because it's not on the slides and I don't have time and energy for that. I leave it, in this case, as an exercise. Or you can just assume that you have no zero divisors.
About this condition, I think it's not necessary. It is not restrictive at all. That everything is generated by A1 because you can always shift your
Yeah, but then you will have two polynomials, one for even and one for odd degrees, which can be non-equal. So if you have a like polynomial ring, but your T has degree 2, then your model is model of even and odd grades. If this has only even grades, then in your model you can have component which has even grade and component which has odd grades, which are entirely independent. And for these two components, the degrees, you would have polynomials, but these polynomials can be different. So the function which is compound from these two functions is no longer polynomial. Because it's polynomial for even, it's polynomial for odd, but these two polynomials are not related. Man, clear? No, it makes sense to think about this. It's so the thing is generated by H1 always, by A1. But if it's not, so you have a polynomial, say C of T, but T has degree, T is A2. So T generated A2, and you have A0 is C, A1 is 0, A2 is T times C, A3 is 0, and so on. This kind of ring. It's graded, right? Then if you have a model over this ring, you can have this would be, in fact, a direct sum of two models. So you have M, you would have M is equal to M odd plus M even. There are two components, because your ring has odd even degree, so it acts on odd component and even component separately. So your function Hm of n would be polynomial for even, polynomial for n even, and polynomial for n odd. This is because, I mean, it will be in fact constant for even and for constant for odd, as we have discussed. Because for models over polynomial ring, this function is constant. But these two constants can be entirely different, because these two models, there are no relations between them. They're not related at all. It's just two arbitrary models. You can put anything here and anything there. There's no relations between this and that. This means that these two polynomials, one for even variables, values of n, another for odd values of n, are not related. So you have a function which is constant in even values and constant in odd values, but these two constants are different, so it can be a polynomial.
This condition, it applies to what?
To A. A is generated by A1.
A is generated by?
A1 and A0, of course. Something you would always have, like for polynomials, for whatever. Questions? So suppose you have a local ring. I can explain. No, I just gave you a counterexample. So it can be true for when it's false for this particular example. Good. Thanks. Okay. Yeah. Okay, so if we apply that to this exact sequence, now we have, suppose that n A is not zero divisor. You have M, 0 goes to M star, goes to LA maps it to M star plus 1. And then you have co-kernel, which is M star plus 1 quotient by A M star. And then you have degree Hilbert function, so HM. The degree of this polynomial is equal to degree of M star plus 1 divided by A M star plus 1. This is part of the same argument that we did. I tried to explain when I gave you this exercise. So every time you do this like integration type procedure for polynomials, you sum up the polynomial in values from 0 to n, it increases the degree by 1. And this gives you a corollary. So degree, well, it's written here. Degree of HM is degree of HM by AM plus 1. Okay. Now I'm going to state you a characterization of dimension of local rings in terms of the Hilbert polynomial. It turns out that we had this Krill dimension, and we even proved that for finally generated ring, Krill dimension is the same as tensorial degree. But it was like in algebraic geometric situation. Typically, if you have local rings, there's nothing like that can happen because local rings are almost never finally generated, even for polynomials. But for local rings, you have another notion which is very similar to dimension, in fact, equal to dimension, as we now prove. So theorem 2. You have R Noetherian local ring. And you take the corresponding graded ring, which is A star, direct sum of mi quotient by mi plus 1 from I equals 0 to infinity, where m is maximal ideal. Then h a of n is polynomial for n very big, and its degree is equal to Krill dimension. Oh, Krill dimension of R, sorry. Yeah. So let's prove it. The first observation is why it is really polynomial. It's almost free to prove. We know that A1 it's one dimensional, it's stupid, it's fine dimensional, of course. Fine dimensional. It's fine dimensional because R is Noetherian local ring. So this is the maximal ideal is a finely generated model over R. And then a quotient by m squared is finely generated over R as well, so it's finally generated over the corresponding over R quotient by M. So fine dimensional should be fine dimensional, sorry. Okay. And the second, also what we have is that if x1 dot xn generate some model over modular over R modular M maximal ideal times M, then x1 dot xn generate M, right? So this implies that M, so if you have this x1 dot xn inside M without M square, generate M without M square, well, generate M, modulo M square, they generate M. And then their products, X, homogeneous polynomials, degree d of xi generate m power d, quotient by m power d plus 1. In fact, they even generate m power d because of Nakayama lemma. You do this by induction, so you know that they generate m modulo m square, but then m square is generated by the same guys, by their products, and modulo m third, they clearly generated, they generate the quotient. Because the quotient so you have m times m mapped to m squared. This is clearly, if you have something generates there and generates there, then this is so you have x1 dot xn generating there, x1 dot xn generating there, then your product is generated by the symmetrics, by xi, xj. They generate m square. Because they generate m square modulo m square quotient by m cube. Well, in fact, these guys generated, this guy generated, so this guy generated this. This is clear, in fact. And then the same is true for all other m. So this is why this graded ring is generated by A1. Probably essentially for free. Except that you need to use Nakayama to make sure that this xi generate m. Then their products obviously generate the square and so on. Okay. Step 2. We take a minimal prime ideal Q inside R, minimal such that. So what is minimal prime ideal? Well, if it is has no zero divisors, it's just 0. But if it has zero divisors, then you take like primary decomposition for 0, and you take any primary, any ideal in this primary decomposition, for instance. If you speak in algebraic geometric situation, then you take the ideal of all functions which vanish on all of your irreducible components except one. This is clearly an ideal, and it is prime because it's the quotient by this ideal is functions on one of your reducible components. They have no set divisors. But anyway, you definitely have the smallest prime ideal because the dimension is finite. This is something we know. The Krull dimension is finite for any Noetherian ring. And in that case, dimension of R quotient by Q is equal to dimension of R. Well, there is a bit of a ambiguity here. So because suppose you have a variety, algebraic variety with two components or three components, one of them dimension say 1, another dimension 2. You have two of these ideals. One of the ideals is functions vanishing on one component, another is function on vanishing on another component. There are two minimal prime ideals, but the dimension is different. Since we are interested in induction by dimension, we'll choose the one which gives us the biggest dimension. You can always do that by definition of full dimension. Okay. And then you define yeah, you have R and R1, which is R by Q. And the dimension, the crude dimension is the same, but then if you look at the growth of your of the corresponding Hilbert function, then this so R is actually finite over, well, R1 is finite over R, but so anything, well, the corresponding degrees grow the same way, because this is, if you localize over this ideal, R1 will become, if you localize R over ideal Q, this will be Artinian. So it's finite dimensional. This means that this is finite, so the degrees are the same. And every time you have a, the growth, just finitely many generators of R, which, so we just use that the R over Q is finite as R mod. So it grows not faster than, so R1 grows no faster than this, but then this is actually, one of them is finite over another. So there's growth can be estimated both ways. Okay. Yeah, so in the end, we replace R bar R over Q and assume that it has no other divisors. This is why I needed a step. So assume that R has no other divisors. Okay. So step 4. Oh, there's one step missing, but doesn't matter. Step 4 is about, we fix a chain of ideals. Well, step 3, probably because step 3, 0 goes to, is not equal to Q1, to P1, sorry, sits inside P2, again sits non-equal in P, and so on, up to Pn. And N is crude dimension. All right, right. Now I remember what is step 3. We can, yeah. So we need to pass to integral closure. This is why we needed this notion. Why we wanted to have no zip divisors. It's because I didn't define U. You can actually do that, but I didn't define the integral closure for rings which don't have zip divisors. So we pass to integral closure. So you have 0 goes to Q1, is inside Q2, and so on. This is because of Cohen-Macaulay lifting of the ideals. This is in R tilde, which is integral closure. Questions? Yes, thanks. Cohen-Zellenberg. I hope here I have Cohen-Zellenberg correctly. Thanks. Okay. Now, R tilde is a finitely generated model over R. This implies that associated graded ring of R tilde is finitely generated model over associated graded of R. And this implies that their degrees, the degree of growth are the same, because this just means that for each particular degree, the dimension of the space associated with R is dimension of the space of R tilde is dimension of the space associated with R times some fixed number. The fixed number, which is the number of the dimension of, this is R tilde is finite extension of R of degree k, and this dimension of a maximal ideal of M of maximal ideal. Well, now our maximal ideal is Qn, so we have Qn power k quotient by Qn power k plus 1 is equal to dimension of p k quotient by pn k plus 1 times some fixed number, which is the degree of the extension. So this grows precisely the same speed as that. If you have two functions which are different by a constant multiplier, the growth of degree is the same. Okay, so I explained that if we pass to the integral closure, the dimension, the Kuhl dimension doesn't change, and the growth of the Hilbert function, the degree of growth of Hilbert function also stays the same. So we can assume that the dimension, the ring is integrally closed. Step 4. We can assume, from step 3 we can assume that R is integrally closed. In fact, if we went so far to define normalization for a ring, which is like integral closure, but not for a ring which is, for a ring which can have zero divisors, we wouldn't need even step 3. Step 2, we would immediately pass from here to the next step, because the rest of the proof doesn't use the integral, the zero divisors in anywhere. Okay, so we have this sequence, and when we take the localization over the smallest ideal, P1, and it's local, Krull dimension equal 1. This is because there's no smaller ideals, and P1 is already maximal because we localized over everything which doesn't belong to P1. So it has only 0 as 0 in P1. And integrally closed, because localization of integrally closed ring is integrally closed. This is because if you have something which is the root of monic polynomial in localization, this gives you a root of a monic polynomial in your ring. They will be different by an element which was used to localize. I mean, and then this would mean that since your ring is integrally closed, that would mean that this element up to something you localize actually belongs to this ring, so it belongs to this ring. Okay, so this is local of full dimension 1, then it is actually principal ideal ring. It's a discrete relation ring. P R P1 is dvr. And P1 is generated by P. Okay. There's a bit of a problem here because there's, I mean, it works only after localization. We don't know if this ideal is principal before we do localization, but still it is principal, at least in our. Okay. And I would choose P. Well, P is of course in P1. At some point it would be convenient to choose it actually in maximal ideal without maximal square of maximal ideal, but let's pass to that later. Okay, what is important now is that if you take the quotient, so we have our chain, and then you take the chain, the corresponding chain in R quotient by P. So R quotient by P has chain associated, so P belongs to this ideal, so it has chain P1, sits inside P2, sits inside P3, and so on. But now, this quotient by P1 is actually a field in RP1. So this P1 is the smallest ideal. There are no, smaller ideals don't exist. Of course, this quotient by P1 a priori it might have some bad stuff like zero divisors or something. This is one more reason to use zero divisors in everything. But at least this P1 now is smallest ideal. It doesn't contain any smaller ideal after you take the quotient by P. Okay, so this is, in particular, this implies that Krull dimension, something that we know very well, in fact, that Krull dimension of, but we did it in geometric situations. If you have a ring and you have an element which is not a zero divisor, then dimension of R quotient by P is dimension of R minus 1. We had that. For finally generated ring, this is precisely, I mean, you can obtain this, for instance, using the transcendental dimension. But here, of course, transcendental dimension argument won't work, but this argument works. Okay. Now we have A inside M quotient by M2. It's a class represented by P. So P, since P generates a principal ideal, it can't lie in M squared. because then you would have some two elements which sit in maximal ideal, and their product is divisible by p, which would contradict to RP1 to p generating prime ideal in RP1. So it belongs. So because p intersected with the ideal p intersected with m without m square is non-empty. It's non-empty already in localization. Okay. Yeah, and then we have, by this corollary which I just erased, we obtain that a dimension, degree of Hilbert polynomial of R quotient by P is a degree of Hilbert polynomial of R minus, not R, but it's A quotient by this generator A is equal to Hilbert polynomial of A minus 1. This is an overhead. So if you take a ring, you take its quotient by a generator of your by an element in A1, which is not a zero divisor, then you have this. Well, it's the inverse for zero divisors. Yeah, it's because of this exact sequence which I wrote. Okay. But then this, now I can erase this. Now I have a chain of equalities which in the end brings what we need. So I have degree H A quotient by the ideal generated by A is degree of H A minus 1, and degree of H A quotient by A is dimension of R quotient by P is dimension of R minus 1. So the non-trivial passes here. This you can obtain by using induction and dimension of Krull dimension. This has Krull dimension definitely smaller than R, as we proved. So, and the corresponding the graded ring associated with this local ring is precisely HA quotient by A, small. Because of this, the A represents P. So by induction, we can assume that this is equal. And then this is the same as dim HA minus 1 as it here. Now we remove minus 1 here and minus 1 there and obtain that dim degree of HA is equal to dimension of R. So the proof is sort of straightforward. You do it as follows. You start with any local ring. You find a generator for smallest prime ideal. You take the quotient by this generator, and for the quotient, you already, it's smaller Krull dimension, but also it's, so you can, using induction, you can prove that the equality, the Hilbert polynomial has the same degree as dimension of this quotient. And then you check that the first, this dimension of this quotient is same as dimension of your ring minus 1. This is just because the corresponding chain of ideals starts with P. But then the degree of Hilbert polynomial of the quotient is the same as a degree of your Hilbert polynomial for A minus 1. This is because of this exact sequence. So this is, the idea is simple, and the only slightly non-trivial part is using integral clause and discrete evaluation ring to prove that this ideal is actually the principal. Okay, I'm done. And so next time I will put online the Google form, which is needed for people who want to pass exams. And tomorrow we'll have the last class. Muito obrigado.